Hello, this is Vedamas, and this is for the purpose of experiential learning for PIC and EC. We're going to be talking about the model, we're going to be explaining the materials and methodology used in the model today. We have built a radar system for a miniature radar system mimicking defense radar systems that are used by armies all over the world to detect unmanned uh, threats such as missiles. But in our use, there are some use cases where the missile also uses to detect an obstacle so that it can fix its path on the target. Suppose the target is moving, changing direction continuously, the missile needs to instantly detect where it's moving, and that's how this is just a small illustration. Now, one concept that inspired this model was something that we call heat-seeking missiles. Now, these heat-seeking missiles are essentially launched at an aircraft like a fighter jet, aiming to, you know, destroy the fighter jet. And the pilot of the fighter jet sees that the missile is coming to attack it and starts to change the direction. So the objective of the missile is to still hit the plane, right? So what it does is it has a temperature map of the whole surroundings, and it goes attacks. It changes its direction towards the hottest place of that temperature map. And in this scenario, the hottest place happens to be the engine of the plane. So whatever happens, that missile will always follow the engine of the plane. Now, why we could not directly implement a temperature model as I just explained right now was because the affordable temperature sensors that are available in the market today, namely the Adafruit DHT11 sensor, it has a 3-second delay to get the temperature, and the temperature readings are not very accurate, and it's not quickly also. It takes a lot of time. Suppose there's a place where the temperature goes from, say, a room temperature of 28 to suddenly say 100, okay, uh, there is a delay, and instead of showing even something close to 100, say suppose it goes from 28 to 70, it doesn't do that. It just goes to 28, 29, 30, 31, 32 every 2 seconds, and it's not feasible to get instant temperature values. So this way we decided on a radar setup using an ultrasonic sensor. So it's more of a sonar setup, but it's displayed on a radar screen. Using sound waves, we try to determine the distance of an object that is around 40 centimeters, and uh, the model is going to be explained by myself, Mustafa, and Harush. Harush will talk about the servo motor and the HCSR04. I shall talk about the connections used in the whole model. Mustafa will explain the flowchart, the algorithm, and the working. Thank you.
My name is Harush Elharki, and I'm going to be explaining the working of ultrasonic sensor and the servo motor today. So yeah, the ultrasonic sensor, which is HCSR04, it has 4 pins basically, which is VCC, trigger, echo and ground. So the VCC pin is given 5 volts by the Arduino board, and the second pin is the trigger pin. When the trigger pin is high, the sensor sends sound pulses, and then at the same time the echo pin is high when the sound pulse is sent, and if the reflected pulse comes back, then the echo turns low and the time is calculated. Time by 2 into speed gives the distance of the object in front of the sensor. The sensor's range is 2 centimeters to 400 centimeters, but we are taking into consideration only like 40 centimeters of range. And if there is no object in front of the sensor, there is no reflection of the pulse. So after 30 microseconds, the echo turns low, and the ground pin is connected to the ground via the Arduino. And the receiver is the place which receives the reflected pulse back. And distance is speed into time. Okay, when I come to servo motor now, servo motor is a DC motor basically, and it has a precision of 1 degree. So when it can, from its neutral point, it can move 90 degrees to the right and 90 degrees to the left. So the range is like plus 90 to minus 90. And we can control the speed of the servo motor because it is based on the principle of pulse width modulation, and by varying the resistance, that is using a potentiometer and the gears inside, we can actually change the speeds according to our requirements. And it has 3 pins, that's the ground, VCC, and the control pin, like in order to change the speed of the motor, we need to give it the right signal. And VCC is where the 5 volt is provided to the motor, and ground is what, the negative ground. Thank you. Understandable only. Action.
I'm Vedram S. and I'm going to be explaining the connections of the model. So first I'll be explaining a block diagram here, and then I will be illustrating the connections. So first, this is an obstacle detection system, right? So first we'll consider the obstacle themselves, where I'll represent using this block saying OBS. Now we have the ultrasonic sensor, which I will represent using ultrasense. And this will send a wave, receive a wave, and those two are transmitted to the Arduino. Now the Arduino sends this data to the computer, and the computer processes this and sends it to a processing IDE, which outputs the given data on a radar. The Arduino also controls a servo motor on which the ultrasonic sensor is mounted. Now I'll talk about the pins that we have connected the Arduino with. Pin 11 is connected to echo of the HCSR04. Pin 10 is connected to the trigger. And pin 12 is the servo control. There is 5 volt, which is the VCC, and ground, which is 0 volt. Yeah. So coming here, as you can see, we have the HCSR04 ultrasonic sensor that is mounted on our servo, and the servo is rotating from 180 degrees to 180 degree span, and the outermost pins are VCC and ground, which is what powers the sensor. We have the trigger and echo, which goes straight to the Arduino, right? The VCC and the ground are connected to the breadboard, where the Arduino's VCC and ground are also connected. They are parallelly connected. The servo, again, the VCC and ground are connected to the breadboard's VCC and ground, and the control goes to the Arduino. That is all with the connections. Thank you.
And I'll be explaining the flow chart for the code of the model. So first, when the code starts, we initialize the pins. The echo pin is pin number 11, trigger pin is pin number 10, and the servo is attached to pin number 12. Then to control the servo motor, we need to take its angle from 0 to 180 and back from 180 to 0. So we initialize I equal to 0. Then we check for the condition if I is less than equal to 180. If true, we write that angle to the servo motor, that is taking it to the angle I. Then we calculate distance from the calculate distance function. I will be explaining that at the end. Then after calculating the distance, that distance is sent to the processing IDE, and is outputted on the radar through the processing ID. Then we increment I and check for the condition again. So this loop keeps running until I reaches 180. Then we take it to the returning part. So I is 180 and we check if I is greater than equal to 0. And the same thing that we did here, we do it here. But here we decrease I from 180 to 0. And then when I reaches 0, we stop it. And this whole code is within the void loop of the Arduino code. So this whole code runs infinitely. And coming to the calculate distance function, here we know the speed of sound, that is 340 meter per second, and we know the time that it took to travel to the obstacle and back. So we divide it by 2 and then we return this distance, which is this. Thank you. So coming to the Arduino code, there's two main parts. One is the void setup and the other one is the void loop. And before the void setup, we include all the libraries. Here the required library is servo.h, and we declare the variables that will be used, that is trigger pin 10, echo pin 11, and we declare two variables, long duration and in distance, that will be needing to calculate the data for the ultrasonic sensor. And we create a servo object for controlling the servo motor. Within the void setup, we declare the pin modes, that trigger pin is going to be the output, echo pin is going to be the input, and serial communication will be at the speed will be at 9600 baud rate. And we say my servo dot attach 12, so we define the which pin is on which pin the servo is attached. The void setup is run once, and the void loop part, it keeps running infinitely till the program is running. So in the void loop part, we have a for loop where I goes from 0 to 180 with an increment of 1 every time, and we write the angle I to the servo, and then we give a delay of 30 microseconds, and we get the distance from the calculate distance function that is defined later, and we print these values to the serial monitor. It's given in this specific format which we'll be using in the processing ID to get the values to be plotted on the radar. And after the for loop, where I goes from 0 to 180 now, we have the servo coming back to its position. So there's 180 to 0, and we do the same thing here basically. And then in the calculate distance function, first we write low to the trigger pin and then give a delay of 2 microseconds. Then we send high to the trigger pin and again a delay of 10 microseconds, and we send low to the trigger pin. Now duration will be given by pulse length of echo pin, giving it a high. So from that we can get distances duration into speed by time, that was explained in the flowchart earlier. And then we return the distance value, which will be used in the void loop part. So looking at the processing ID code, this code has been written in Java. First we start off by importing the required libraries. First one is processing.serial for serial communication. Then we have java.awt for making the UI for the radar plot. And then we have input output exception, that is error handling. We create a serial port object. Then we declare the required variables. Then in the void setup part, we declare the size of the window and the serial port through which the data will be sent, and the baud rate, which is 9600, same as what was mentioned in the Arduino code. And we keep reading until the serial port sends a full stop. Now in the void draw part, we draw the radar, the lines, the object that will be in red and the lines will be in green, and then we have the necessary text for labeling. In the void serial event, we read the values that are being sent through the serial port in the same format that was mentioned in the Arduino code, and from that we are getting the angle and distance values. And in the void draw radar part, we are drawing the necessary lines for with the given width for drawing the radar. And in the draw object part, if the distance is less than 40, then we draw the object that will be in red color. And in the void draw line part, we'll be drawing the green lines that will be when there is no object being detected. And in the void draw text part, we'll be making the necessary labelings, that is for 10, 20, 30, 40 centimeter, and displaying the angle and distance and making the text boxes for that. That is it. Thank you. Now I'll be demonstrating the working of the radar system. Over here we have the radar from 0 to 180 degrees, and it displays the angle and distance here. Distance is displayed when the distance is less than 40 centimeter, and we have radial lines showing distance 10, 20, 30 and 40. So let's say there's an object here. When the sensor faces it, there's red lines showing at what distance it is. So it's around 20 centimeters, and between these angles. And now let's say if there's two different objects. When the sensor comes back, it detects both the objects separately and at what distance they are. So that's it. Thank you.